Hey there, AP Pre-Calc. We're looking at lesson 2.6. This is our second day today. We're going to look at appropriate regression models for data sets and competing function model validation. We want to observe both the residual plots and the endpoint behavior whenever we're choosing an appropriate model. If the residual plot follows a regular pattern, then there is a behavior that's not accounted for by the kind of function that's chosen. But if the residual plot has no identifiable pattern, then the regression equation most likely will model all but random fluctuations in the data set. And that's what we were noticing on the first day. We were looking for residuals that were randomly scattered along the y-hat line. In example 7, we see your biology teacher has bacterial cultures for a class of 24 students. And each student is measuring the number of bacteria, Y, in his or her culture at intervals of time, X hours during the day. The results are shown in the table, and a scatter plot is given below. And we want to find a power function regression model and also an exponential regression model. In yesterday's lesson, I was using the TI-84, but since the Desmos graphing calculator has been added into your ability to use that calculator in the online model of the test, I want to explore the Desmos calculator today. So you can see the first thing I needed to do was make a table. I typed into the first line table, and then an X1, Y1 table pops up. And my job was to enter all of that data into the table for the example 7. Next, we want to be able to write a power function as a regression model. So let's think about that. So to get a power function, that would be y equals ax to the b. So I need to type in y sub 1 and put the tilde mark because that's going to be a regression equation. Y sub 1 is approximately ax sub 1 to the b power. Now I get regression parameters right here, and I notice that the r squared value is 0.9448. But if we enter into the log mode, so if I press the log mode here, let's highlight that. You notice that the r squared value is a little bit better approximation. So our power function is going to be 291.96386. And then our x with the 1.22079 for our power. So let's go record that on our notes. So the power function is y hat, is 291.963 8x to the 1.22079 power. And then we want to find an exponential regression model. So back to our graph again. Make that larger. An exponential regression model is going to follow the form y is ab to the x power. So we're going to go in line 3. And we're going to type in y is approximately ab to the x power. So same thing again, if you look at the r squared value of 0.9307 and you click on the log mode, we're going to get a better r squared value in log mode. If I could get this to cooperate with me. So we're going to keep that log mode on, and you can tell our regression, the A value is 180.65764, and the B value is 1.6 9938. We want to go record that on our notes. So the exponential model, y hat, is 180.6576, and we've got 1.69938 to the x power for the regression model. Now, part C says discuss the right end behavior and the left end point behavior in relation to the regression equations. Which model would better represent the data set and why? So I'm thinking that because the graph is showing us that the second equation actually passes through 0, 0. And this is a set of bacteria. So we had to have some initial bacteria. I would say that the red equation, or the AB to the x power, that exponential function, has the better model. Since both of them model the behavior pretty well, they both have the increasing and the right endpoint behaviors are both the same, but only the exponential function has a left endpoint that's going to be a non-zero value that would model some initial bacteria present when the teacher gave each student their culture. So you can read how I summarized my findings. In part D, we want to use the exponential model and find the number of bacteria in the initial sample. Then we want to make a prediction for the number of bacteria present at 24 hours. So our job now is going to be to enlarge our graph, and we're going to need to write the equation in so that we can use the calculator to estimate for that value that they're asking us for. So give me a minute to set this up. So in the fourth line on my Desmos calculator, I've entered the values 180.65764 and my base 1.69938. And what do we want to do? We want to evaluate the y of 0. So let's ask the calculator to do that for us. You see the f of 0 is 180.657, and then the f of 24 is, ooh, that's a lot. What, 60,789,462 bacteria. So let's record that on our notes. So we got the y hat of 0 is about 180.658, and the y hat of 24 is roughly 60,789,462.320 bacteria. And then lastly, when will the number of bacteria reach 10,000? So what we need to do there is we need to go back to our graph and let the calculator estimate that for us. So we're going to bring this back down here. And here you can see I've graphed g of x is 10,000. This is our green line. And then in line number 8, I want to know where f of x equals g of x. And then hovering over that, you can see that happens at 7.569 hours. So we want to record that on our notes. So we know that during the 8th hour, the bacteria will reach 10,000 as far as population goes. In example 8, we're driving down a dirt road. You puncture a tire of your truck, and the table shows the pressure measured in pounds per square inch. If the air in the tire at any time given is measured in seconds after the tire was punctured, We want to find an exponential function in the form of y equals ab to the x that best fits the data. So again, let's try this with the Desmos graphing calculator. So by typing the word table, x1 and y1 pops up, and our job is to fill the table with 5, 10, 15, 20, and so forth, all the way down. 15, 20. We're going to go up to 50, 25, 30. So we got the entire table done. Now go to line 2 on Desmos, and we want to enter in that we're going to find an exponential function in the form of y equals ab to the x. So we want to type that in. We've got f of x is approximately a b to the x sub 1 power. So f of x sub 1 is ab to the x. I take that back. It needs to be y sub 1 is approximately ab to the x. Again, I'm going to check the log mode. So r squared here is 0.9972, and out of log mode is a little less efficient. So we're going to use this at 35.515. Let's see. I guess my TI-84 calculator used the log mode. So we're going to have 33.8795, and the B value is 0.955137. I'm going to record that on our notes. 33.8795 and 0.95514 to the x power. We want to plot the equation in the scatter plot on the same screen. Does the exponential function fit the data points, and explain? And we just looked at that, so yes, the data points fall along the curve of the regression equation. So we can write a sentence about that. The data points fall along the curve of the y-hat, or the regression equation. Now going on to part C, can we use the model? We want to know what the pressure of the tire was before it was punctured. So let's take a look at that using that model. So using the model, it looks like the pressure was 33.8795 at the time that it was punctured, or about 34 psi. Now, on the Desmos calculator, if you press this button, you can graph the residuals here. I know that it's showing up on our set of notes too, and it says the residual graph is shown at the right. What does it tell you about the validity of your regression model? And I would say something along the lines of the residual graph has no identifiable pattern. So this is a good model for the data we were given. Something along that line. For example 9, they're giving us a set of data that has an upward trend shown in the plot below, and it's not clear whether the best fit function is linear or exponential. And our job is to use the residual plot to determine which regression function would be best to model the data set. So looking at the first one, the linear function residuals, those are seem to have a pattern there. They're high on the sides here, high on the sides, and then low in the middle. So I see some kind of a pattern like that. that would tell me that's not a very good model for the data. And the exponential function, the residuals, are random. So in my opinion, the exponential model would be better. This is the best model because the pattern's random. And the linear function model is not a good model because there's a pattern there with high on the sides and then low and then high. So it may be because it's non-linear data that was given, even though the data set kind of looks like it could be a line, it behaves more like exponential. 2 point, great. 0.2, 135.2, 153, 167.5, 172.6, 182, 182 and a half. Wait. 182 and a half. No. 187. 180.8. 193.8. 230.5. Okay. Cubic regression. No. Y1 is about cubic. AX1 cubed plus BX1 squared plus CX1 plus D. -5 to 30. Okay, for example 10, we have a textbook publisher that prints textbooks in thousands of units. at a cost in thousands of dollars. And we've got the table here with the cost here, and our job is to find the average rate of change in the cost from 10,000 to 13,000 books. I've already worked that out. 13,000 is 167 and a half, and 10,000 is 153. So the rate of change between 10 and 13,000 is 4.83 repeating. 4.83 repeating in thousands of dollars per book. And the average rate between 18,000 and 20,000 is 2.6 in thousands of dollars in thousands of units of books. For part C, we want to find a cubic regression model for the data set. So I've already pre-worked that in my Desmos calculator. Pull this up. Here we're looking at the table. We've got the table, and in the second line, I've written the standard form for a cubic model where ax sub 1 cubed, bx sub 1 squared, cx sub 1, and then plus a constant. And you can see our model is about 0.9425 on the r squared term. Here's our A, B, C, and D values. So we want to record those on our answer key for our notes. And here we have the solution for the regression equation we got from the Desmos calculator. Looking ahead on part D, does a residual graph indicate that this is an effective model? So we could go back to the calculator and ask for the residual plot. Looking at that plot, it appears like these are randomly scattered. So yes, the residuals are random and they lie close to the horizontal axis. Then to finish up this example, we know that the residuals are random, and the cost to, if no books are printed, would be to evaluate the regression at 0. So 75,000 dollars if no books are printed. That would be something we would consider to be operating expenses. And if we use the cubic regression model and predict the cost to print 24,000 textbooks per week, substituting 24 into our regression model is close to $195,000 to print 24,000 books. This lesson is running long, so let's go through example 11 rather quickly. We have the demand for motorized scooters in a large city center, is shown in the table below. And for 30 days in the study, each day's scooter demand is given in the calendar. For example, on day 1, there was a demand for 35 scooters. This was the temperature for the day. We want to find the best regression equation model for the data set and explain your reasoning. So without knowing anything, I looked at the scatter plot first and found that it seemed exponential. So I used that and compared the residuals. And I don't have the graph for that, but I did get the best regression equation model, and I've written my answer from Desmos here. And I said the reason exponential was best was because the left-end behavior, as you went to 0, the y value went to a number value, not to 0. For part B, the city wanted to remove the outliers in the data for the scooter demand. And I picked 5 outliers for myself. I highlighted those above. We're going to use the residual values. The residuals will help us justify our choices. Now, like I said, because of time of the lesson, I've done all the work on the side. But 75 degrees and 83 scooters had a very large residual, 32.872. It was underestimating. These were underestimates, and this was an overestimate. if you go back and remove those outliers and recalculate the regression equation, did it improve the model? Well, after I did all of that, my new y hat equation turned out to be 4.0450. The base was 1.0322 to the x power. And yes, it did improve the model because the errors are closer along the y hat equals 0 line now. So we could say something along that line. Yes, this improves the model. Because the errors are closer to the y hat equals 0 line. And then finally, what other type of analysis could the city explore to better understand the demand for the scooters? And my idea would be that they could consider maybe colder temperatures. So that could be one factor, colder temperatures. They could also consider what happens on the weekend. Are there any kind of events that are occurring? Could the weather, maybe rainy days? Rainy days could cause a demand to go down. If it's summertime, the humidity or the cold, and also possibly if there's some big conference in the area, if they were being hosted, that could affect how many scooters would be needed. So those are some of the other analytic options that could be considered. That's the end of lesson 2.6. Lots of calculator options for us.